Let's move on to understand decision trees. So decision trees are a class of supervised learning algorithms which can be used for predicting categorical as well as continuous variables. So how does it work? It works by breaking down data from the root node into smaller and smaller subsets while incrementally building associated decision tree. Now the final result is a tree with a root node, a couple of decision nodes like windy and humidity over here, and then finally leaf nodes. Now, decision nodes are the nodes where we create a rule and we actually get the end result using the leaf node. Let's simplify this. So the decision tree in front of you is created for a simple use case where you're predicting what are the chances that a match, it's a football match, will be happening in the stadium, yes or no. There are three attributes that you need to consider. Outlook, which could be sunny, overcast, or rainy. Windy, which could be true or false. And humidity, which would be high or normal. Now, based on these three attributes, outlook, windy, and humidity, what are the chances that a match will happen in the stadium today? So, if you go back to the same algorithm, what happens over here is the algorithm creates a root node. Now, out of these three variables, outlook, windy, and humidity, one of them is selected as a root node. Now, let's keep it aside for a moment that how is the root node selected to understand the remaining algorithm. We'll come into the details of this later. So assume that based on some criteria, it chose one of these variables, let's say outlook, as a root node. Then it creates three partitions because outlook has three values, sunny, overcast, and rainy. So let's say at the starting point you have 100 records. And these 100 records get partitioned into 20, 40, and 40. Cumulative all of them will become 100. Now, at each node, the algorithm tries to understand whether is there a need to further split it. So if you look at sunny and you compare your end outcome variable, which is let's say the chances that a match will happen or not. So you'll have values like yes and no. So there is a scope over here because out of the 20 records that have gone into this, let's say 10 would be yes, 10 would be no. Over here, 40 records are present, out of which let's say all of them say yes. And over here, out of rainy, which is again 40, let's say 20 would be yes and 20 would be no. Now, over here, since all of the answers are yes, there's no need to go further. So we stop the algorithm over here for this decision node. So this would be a decision node and this would be root node. Over here, for sunny, we'll have 20 records. 10 of them would be, let's say, yes, and 10 of them would be no. So we use the next variable. So we have already expanded outlook. Now we take the next variable, which is, let's say, windy. Now based on our algorithm, we would, let's say, prioritize them as outlook, windy, and humidity. So we start with windy. Now we start with windy. We'll say, we'll put it under sunny. And we'll say, okay, fine. How does it look like? We'll partition the dataset under sunny across the attributes for windy. So we have 20 records over here. That gets segregated into the records over here. So let's say 10 of them go over here, 10 of them go over here based on the answers of yes and no. And once you reach false, all of the values over here are yes, and all of the values over here are no. So you terminate these nodes. These become leaf nodes and these become decision nodes. As you go on towards your right, you have another variable which is humidity. Now you put humidity under rainy and then split it across the different values it has and then and then terminate them based on the values. Now, had there been a scenario where we would have, let's say, so this would have ideally 40 records. Out of 40 records, let's say 20 came over here, 20 came over here, and all the 20 over here would have no, but then all the 20 over here didn't have yes. Some, let's say 10 of them had yes and 10 of them had no. Then you would go ahead further with one more variable if it is a scenario, and then further create a classification over here. And in this process, so you start with a small data set and you keep partitioning the data set across with the help of variables that you have selected. Now in this case, you have selected outlook, windy, and humidity in the specific order based on some criteria. We look at the criteria later on. But then to get the crux of the equation, you understand this is how basically you create a decision tree. Now, once you create a decision tree, this is nothing but a simple rule engine. So let's say you have a record where the data set says the outlook looks rainy and humidity is very high and it is quite windy. Windy is true. So what is the chance that the match will happen or not? So you run through this tree. You come to Outlook. You say, what does the Outlook say? It says it's raining. So you come over here. Okay, now it's raining. It's asking for humidity. What is the humidity? Is it high or is it normal? They're saying the humidity is high. Okay, if it's high, the chances is that the match won't really happen. But on another scenario, you're saying, okay, fine. For the Outlook, when it says sunny and it says windy, is false. What are the chances that the match will happen? So you run through this Outlook, sunny, okay? And what does it say for windy? Is it false? Yes. So there's a very high chance that the match will happen, right? Now, this is a basic decision tree. Now you could use a decision tree for a classification algorithm or a regression algorithm. Now in this scenario, over here, the leaf nodes, all of the values inside each of these leaf nodes will have the same value. So you're taking a vote over here and you're saying, okay, fine, this node corresponds to yes, and this node corresponds to no. But then had it been a regression use case, you would have something, let's say, like what are the chances that what is the score of the team? How many goals will the team score to place first? And based on some criteria, you'll come over here. You'll say, here we have chances that first team will score 8 goals. Or you tell me that the chances that the number of goals scored by the first team will be 5. Now, since over here it's a categorical variable, you would have all yeses and all nos in case of regression outcome. Here we'll have a couple of different values, let's say 5, 6, 7, 8, 9, and we'll take an average of that, and that average will be the result when you run through a rule falling in this place. So we have basically understood what is a decision tree, what can a decision tree do, and how it works. And we have kept a few things aside as abstracted terms. So we understand that one of these variables are selected as root nodes. There are a couple of decision nodes and leaf nodes. What we don't understand is how is the root node selected and how is the algorithm proceeding further, like on what basis is the next target node selected. We'll get into the details, but then let's look into additional details on decision trees. So there are different types of decision trees. Now, both of them can definitely do classification and regression. Then the most popular names that you would come across in the market would be ID3, CART. CART stands for Classification and Regression Trees, C4.5, and there's a newer one which could be called as C5.0. Now, the basic differences between these algorithms. So the high-level structure kind of remains same for all of them. Now, what differentiates between these three algorithms? One of the differentiator is how is the root node selected and how are the consequent nodes selected. There's a technique to understand why is a particular node selected as a root node. That would be a technique which would be different across all three algorithms. There would be another technique where you would actually handle numerical and categorical variables. So if you look over here, Outlook, windy, and humidity, all three are categorical variables, right? But what if we had a numeric variable? Let's say what if we had something like temperature. Temperature would be a numeric variable. So some of these algorithms won't be really able to handle numeric variables. Some of these algorithms would be able to handle numeric variables with a couple of transformations. Now, what are those transformations? Let's keep that aside for now. Then we could talk about missing values. Some algorithms would be trained to understand how to handle missing values. Some of them might not be. So the differences between these different algorithms would be the kind of technique that they use to select the root node and the consequent nodes, the technique to handle missing value data, the ability to handle continuous data, the ability to handle like a categorical variable with more than 2 levels, and so on. So if you keep aside all of these things, we have 3 popular algorithms where you can say CART is kind of a very popular algorithm these days. So most of the implementations which you see in R and Python are kind of based out of the CART implementation. Now, let's take a simple example and then understand those questions which we have missed in the first slide, like how is the root node selected and how are like how is it different when you're selecting for a regression use case and a classification use case. So we'll understand. We already have understood the basic process. You're building a decision tree, you select the root node, you partition the data into respective groups, you create a decision node, again you partition the data into respective nodes, and you keep repeating this till the node size is greater than the threshold or features is equal to empty. Now, okay, here are a couple of questions that you would have. how to select the root node, how are decision nodes ordered, how does branching stop, and how does continuous variable get treated, and how different is the process for classification and regression. Fair enough, like quite exhaustive set of questions which we have for decision trees. So let's introduce a term called entropy. Entropy is the measure of homogeneity, like it measures the homogeneity of a sample. It can be defined as the formula given minus P log P minus Q log Q to the base 2, where P is the probability of an event happening and the probability of an event not happening. Q stands for the probability of an event not happening. So Q would be nothing but 1 minus P. Now, how do you calculate entropy? So consider the use case which we discussed long back while understanding machine learning. So you have an algorithm which kind of predicts whether an employee is a techie or a non-techie. And you have just one attribute to that is dress code. You'll have formals, business casuals, and casuals. Now what entropy does over here is, entropy first calculates the overall entropy, which is between the end-dependent variable. So it calculates entropy between techie and non-techie. It leverages the formula minus P log P minus Q log Q. Now 46 and 15, this would approximately give me 0.75. It is not exactly 0.75, it is approximately 0.75. But then we just use a simple number for calculation. So we'll say had the probability of P been 0.75, Q would have naturally been 0.25, and then when we put this into this equation, minus P log P minus Q log Q, we get 0.8. So minus 0.75 into log of 0.75 minus 2.5 or 0.25 into log of 0.25, and the resultant value is 8. Now we need to calculate something called as information gain. Now information gain is given as entropy of the employee, which is entropy between techie and non-techie, minus the entropy of the attribute we're considering right now with respect to the outcome. So entropy of employee, which has values like techie and non-techie, minus entropy of the dress code with respect to the employee. And entropy of dress code with respect to the employee can be calculated as, let's say we have three values over here, formals, casuals, and business casuals. And if we divide them further into techie and non-techie, this is how it looks like. So we have total 14 formals, out of which 6 of them are techie and 8 of them are non-techie. And for business casuals, we have 12 values, out of which 9 stands for techie and 3 for non-techie. Add them all, we get 61. So we say entropy of employee versus dress code can be defined as probability of each individual values into the entropy of those respective values. So we'll say probability of casuals into entropy of casuals plus probability of formals into entropy of formals plus probability of business casuals into entropy of business casuals. So it's a summation of probability of a class multiplied by the entropy of the class and summate it for all the classes in that particular category. So in this case, we have three classes, formals, casuals, and business casuals. Now if you leverage this formula and you put in the values, so probability of casuals, we will have probability of casuals as, okay, this should be, one second, I'll just make a small correction over here. Okay, this just got reversed over here. I'll just make it simple. So let's just follow the same process, formals, casuals, and business casuals. So this is formals, yeah, now it looks better. And then you have casuals, and then you have business casuals. So probability of formals would be 14 by 61. So you have 14 formals divided by the entire sum 61 into entropy of formals, and that would be 6 by 8. So you repeat the process for probability of casuals into entropy of levels in casuals, and then the same process for business casuals. So you get 0.68 if you do the math. Now the way you expand this, that is entropy of 6 by 8, is the same way you did this for employee levels, techie and non-techie. So you do minus P log P minus Q log Q, and you find the value over here, and you multiply it by the probability of formals. Add up all of them, you get 0.68. Now if you calculate information gain would be entropy of employee minus entropy of dress code versus employee, and you get the number 0.11. So we say 0.11 is the information gain of the variable dress code against employee. Now the same process can be leveraged. So let's say if you have 5 different variables in this entire exercise, I can calculate this information gain across all 5 independent variables across the dependent variable. So the dependent variable over here is the employee, which will be techie or non-techie. And let's say just like dress code, you could have another, let's say you have another variable, which would be, let's say, gender or location or department. And you can calculate the information gain across all of them and then look at which attribute or which variable has the highest information gain. Or the attribute with the highest information gain is selected as a root node. And the second highest attribute with information gain is selected naturally after you expand the root node. So the process of going from the root node to the leaf node, you'll select the root node and you'll pick up the next attribute in the sequential order. Now that sequence is determined by information gain. So let me just summarize this. We are talking about what technique do we use to identify the root node and the consequent nodes. So over here, we defined 2 measures. One is entropy, and through entropy, we define information gain. And we're saying information gain is the criteria used to understand which would be the root node and the following subsequent nodes. And we define entropy as a measure of homogeneity, which can be calculated with the formula minus P log P minus Q log Q. The Q is the probability of the event not happening, and P is the probability of the event happening. We took a simple example and we understood how to calculate entropy for the outcome variable and entropy of the outcome variable in accordance with one of the attribute. With this, we further go ahead and calculate information gain. Now, information gain is the end criteria which can be used to go ahead and understand which variable could be selected as a root node and the consequent nodes. Now, this is one of the available techniques to identify the root node and the consequent nodes. There are several other techniques available, Gini index or node purity, and there are many more alternatives available for understanding what could be used to select the root node and the consequent nodes. Now, each of these techniques differ in the way they select the kind of the base algorithm for selecting the root node and the consequent nodes. The one which we just discussed is exclusive kind of for ID3 when you're considering about classification. Now, if you've understood this could only be leveraged in a scenario where we have classification problems. You're differentiating between a techie and non-techie. Had you trying to be experiment to understand the prediction where you're trying to predict the number of years a company would stay loyal to a company, that would be a continuous problem. So you would have a numeric variable. So in that case, entropy and information gain won't be really useful. You would need to use a different measure. Now, we won't get into the details of what is a different measure, but I'll give you a simple example saying that is called as standard deviation reduction. I would recommend you to explore standard deviation reduction. So just like information gain, we have standard deviation reduction, which can be used in ID3 for regression. So you move from you select the root node and the subsequent nodes based on the criteria of standard deviation reduction. So let's look into a basic example. Now, the moment you go from the root node to the leaf nodes, you go on the basis of lower entropy. And the moment this is a case of classification. And over here, you can go for, in the case of regression, you can go for lower standard deviation. Now, this is an example I've just put over here to understand what could be a use case that where you can determine the employee's average working hours. And it's the same, we have pretty much the same variables. We have dress code and we have gender. We have 2 variables over here. And as you can see, let's say we have 100 variables, 100 records initially. It's partitioned into 25, 20, and 55 because that is how data looks for casuals, business casuals, and formals. Now, the moment you reach casuals, you have 25 records. Now, 25 is basically a number which you take as a threshold. Since this is a regression, you take 25 as a threshold. So you'll say you won't split a node further until you have more than 25 observations. So you terminate this over here. Now you see over here, business casuals also has, let's say, 20. So you terminate that over here. So this number 20 or 25 is a number threshold which is chosen by the algorithm automatically, or you could override it. Let's say had the number been 20, You look over here, formal has around 55 observations. So that's above the threshold. So you need to like break this down further. So you take the next variable in place. That's gender. Gender will be split into male and female. And then over there, you take the values as male, where you have 32 observations, and you take the value of female, where you have 23 observations. And then you probably have a cutoff, which determines that you don't need to take this further. And at each of these cases, at the leaf node, you take an average of all the records over there, and you get the corresponding values. Now, if you run the algorithm, you're saying, okay, fine, what is the average working hours for an employee who wears formal dresses and is a female? So you just run this algorithm and say, okay, fine, the dress code is formal and the gender is female. So we have approximately the average working hours looks like 8. But then let's say the dress code would have been business casuals. Seems like the average working hours would have been 9, and so on. The same analogy can be extended over here, but then over here, instead of taking a criteria to create a create a leaf node as the total number of observations in that node, you can actually create the number of classes. So over here, definition is okay. In casuals, the total number of classes is only one, techie. Had it been techie and non-techie, you would have still need a scope. You'd still have scope to divide that further. So when you reach over here, formal over here, you still have, let's say, around 55 observations, and you still have around you still have two classes. You have techie as well as non-techie. So there is scope to partition them further. So you take the next subsequent variable from the list, gender, partition it, and then go on. Now, had this the case been, let's say, within male, you still have techie as well as non-techie. You could have created another variable. You would have taken the next variable, which you don't have in this case, and tuned it further. So that's a basic understanding of decision trees. We can do classification as well as regression. We'll quickly take an example in Python to understand how we can build a classification and regression tree, a decision tree for a very simple use case. Let's move to Spider.